Hi, this is lesson 18 in the use of JASP, and today we're doing an introduction to factor analysis, and there'll be a couple of videos on this in order for us to get the hang of what's going on. So we're going to start by going and open down to the data library, and we're going to go and take a data set from reliability and fear of statistics. And this is a data set that we've used before for reliability. And the description of this data set, it's a fictional data set on fear of statistics, has items such as statistics makes me cry, I dream that Pearson is attacking me with correlation coefficients, I don't understand statistics. We get an idea of what these 1, 2, 3, 4, 5, 6, 7, 8 items are doing. We don't have an idea of what the rest of the items are doing. I'm not going to focus on reliability though, as we've done that previously. We're going to go to factor analysis. We're going to go to one of the most common factor analysis done in psychology, which is exploratory factor analysis. And the first thing I want you to see is that this module automatically shows you the R code. If you're looking to see what the R code is and you want to see how to change it up, you can change up your options here. It'll change the R code for you. So that's cool. I'm going to highlight all of these variables. There's 23 of them. I'm going to stick it over here in variables, and it automatically just starts running a factor analysis to get a solution, and it gives me factor loadings. That first factor that comes up here, by the way, is the same factor as what's up here. There's 8 variables, 1, 3, 4, 5, 16, 21, and here you see 1, 3, 4, 5, 16, 20, 21. It's the same variable. So this is where Andy Field is deriving that factor that led you through on the reliability in a previous lesson. He came up with 4 factors. How did he determine that? There's a couple of options here. One is what's called parallel analysis. That's probably the gold standard these days, and we'll talk a little bit more about that. It is best to do this on the basis of principal components, even though we're doing a factor analysis. So principal components is related to factor analysis. They often give very similar results, but if you push this, you're likely to get more factors than what you want. Let's see what happens here. Yeah, we got 7 factors, and that's really too messy. It's more ideal to do your parallel analysis based on the principal components. I'm not going to try and detail why that is, but that's the standard that you want to use. The older standard that SPSS automatically uses is the eigenvalue rule. This analysis, I think, is coming up with, the parallel analysis is matching the eigenvalue rule. Eigenvalues basically are a conduit for calculating the proportion of variance accounted for. And so it's basically saying there's a somewhat substantial amount of variance to be accounted for by this factor. And then you can also manually select the factors. So if I wanted to manually select 3 instead of 4, if I had some reason to want to check that out, then I could do that. But the best way is to go with parallel analysis based on principal components. Let's go and look at analysis options. For analysis options, you have the choice between what's called an orthogonal rotation versus an oblique rotation. A orthogonal rotation is one where the factors are kept independent of one another, and that means they're at 90-degree angles from one another. So if you took X and Y as a coordinate plane, movement on X does not influence movement on Y at all. That is orthogonal, unrelated. Oblique, you might remember back to geometry, the idea of an oblique triangle. An oblique triangle, what is an oblique triangle? It's one that has no right angles. So it's a non-orthogonal. It means that it's allowing for correlations. So these factors here are not unrelated. They're correlated with one another. What is the factoring method? It's using minimal residual right now is its default. I like either principal axis factoring or maximum likelihood. And so maximum likelihood estimation has become increasingly popular with the advent of structural equation modeling. And they're likely going to give you very similar results. We're not going to try and dissect the differences between those. So if you look at output options, there's a number of things here. You can find the structure matrix, the factor correlations. I like the idea of factor correlations. Because if we're doing an oblique rotation, that's where we're allowing the factors to be correlated. And you can see that they're correlated here. You can see that factors 1, 2, and 3 are pretty strongly correlated. They all have correlations of 0.5 or above. Factor 4 is negatively correlated, but those correlations do look adequately sizable to say that, it's definitely related. I believe that what's happening with factor 4, my guess would be here, is that when Andy Field came up with his items, he didn't he came up with a number of reverse coded items. You notice in this one here, standard deviations excite me, and said that was reverse coded. And so that comes up with a negative over here. Here, these factor loadings are coming up as positive, but they're all negatively related to the remaining factors. And so I would guess that this factor, factor 4, is full of reverse coded items that are expressing positive views about learning statistics. You notice that there's a 3 variables here that don't have loading shown. By the way, what is a loading? What are those numbers? The loadings are best thought of as correlations of the item with the factor. And so since these factors are representative of the items, to oversimplify, they should be strongly correlated. And so you expect for factor loadings typically to be reasonably strongly correlated. You want the bulk of them to be 0.5 and above. It's okay if there's a few that are 0.4 or 0.3, but you typically want them to be 0.5 and above. You'll notice the default here is for them to show you the factor loadings for 0.4 and above. There are some people who basically swear by 0.32 and above. And if I change it to 0.32, I get more loadings over here. You notice that if I drop it all the way down, it's spinning. Now it loads up with numbers all over the place, making it hard to see the patterns because a lot of these correlations are exceedingly small. I don't really care about correlations of only 0.05 when I have the factor being defined by correlations that are strong for the most part. So to get a clear view of the patterns, we want to increase that and increase it more. And as we increase it more, we see the patterns emerging. And here at 0.29, I can see, correlations on each of the factors. I see that there's on this item right here, that it's kind of wanting to load on both factors. You notice it loads negatively on this one, which is about fear of statistics. It loads positively on this one, which, I would view as confirming my view that factor 4 is positively viewed items. Let's take a look at just a couple of other plots. Let's go ahead and do a path diagram and the scree plot. Okay, up over here, we chose the number of factors based upon this parallel analysis. What is that parallel analysis? Here it's showing you a scree plot, which is a plot of how much variance the items are accounting for via their eigenvalues. And you'll notice that the first factor is accounting for a lot of variance. And in fact, you can see up over here that initially it has an eigenvalue of 7.567, that it accounts initially for 32.9% of the variance in all of the items. The next one accounts for 5.6, the next one after that 3.9, and the next one after that 3.1, and then it gets a little bit too small. Once the factors are rotated, whatever that means, you'll notice that rotation ends up resulting in the variance being split a little bit more evenly across the 4 factors. Along with the idea that it's made more interpretable. Now, the scree plot is telling you how many factors to retain, and it does that by generating, based upon sample size and the number of items that you have, 23 items, it generates random data. And from that simulated random data, though, even with random data, you would expect with enough measures to get correlations between some of the measures just by chance that would give you some degree of commonality. And if it's giving you some degree of commonality, that's where the simulated data is above those eigenvalues 1 and then going on down. The parallel analysis basically gives you the actual versus the simulated, and the rule is that if the number of factors 1, 2, 3, 4 is above the simulated random data, then you retain those factors, and then once it goes down to be even or below, then that's just noise. It's just noise, just like random data. So this indicates that there's 4 factors. The 4 factors get represented in a diagram like this. These double-headed curved arrows indicate correlations between the factors, which we allowed and which are over here. We allowed it by specifying that we wanted to do an oblique rotation, and the type that we did was called a Promax rotation. And then you have the strength of the loadings represented with each of these circles representing what are called latent constructs that are hypothesized to be causing the score on the items. And hence, since it's hypothesized as a common factor that's causing responses on the items, the arrows go from the latent constructs over to the common factors. Okay, Well, we're already over 15 minutes, and this was just our first introduction to factor analysis. Hopefully that gives you a feel for what's going on, but there's more videos to come and a lot more needed to put this all in focus and all together. We'll talk to you later.